Hello everyone, welcome to this week video tutorial. Today's topic is a work example of 4-bar linkage. So we'll analyze position, velocity and acceleration using vector loop approach. So if we just look at this video, we can find that these point and these point are fixed. So the connected link of these two fixed point, we can say this is a ground link or link 1, which we can, the length of this link we can say D. From this video we can find that this link is actually driver. So this is our link 2, which is input link, and the length of this link is A. The link of that one which connects input and output, so we call it a coupler link, and we consider this as a link 3. The length of this link is B. And finally, this is output link, link 4. The link of this output link is C. So let's consider that ground link length is 5, input link is 2, coupler link is 3.5, output link is 6. The input angle for this 4-bar linkage is 45 degrees, and angular velocity of input link is 8 radian per second, and for input link angular acceleration is 0. So if we draw this diagram, then look at the problem statement, which says all the dimensions are in millimeter, angles are in degree, and you are asked to find angular velocities and accelerations of coupler and output link. You are also asked to find velocities of pin joint and accelerations of pin joint, which in other sense meaning that you're asked to find omega 3 and omega 4, which is angular velocities of link 3 and link 4, and alpha 3 and alpha 4, which is angular acceleration of link 3 and 4. VA and VB are two linear velocities of two pin joint. This is one pin joint A and this another pin joint B. So you're asked to find linear velocities of this pin joint A and B. Also you're asked to find linear acceleration of these two pin joint. Okay, so first of all, position analysis. Even though we are asked to find angular acceleration and angular velocity, our first step would be to find out theta 3 and theta 4, which is coupler position and output position. So first step is to calculate link ratios K1, K2, K3. I have calculated and just presented here the values I got. For step 2, we need to find intermediate parameters A, B, C, and the equations are given to you, and after calculation I found these 3 values. So in step 1 and step 2, you don't need to remember these equations because these equations will be given to you for the calculations. In step 3, we need to find theta 4, and step 4, we need to find theta 3. Before we go to step 4, we need to find out which configuration is our system or 4-bar linkage is. If we just look at this diagram, and we can find that the angle is in first quadrant. I also checked that this 4-bar linkage satisfies Grashof condition, and the input link or link 2 is the shortest link. So the adjacent link of this shortest link is link 3 and link 1. Now in this diagram we can see that link 3 and link 1 do not cross each other. That means the system we are solving is an open configuration. Now I'll show you theta 4 equations for open configuration and cross configuration. So for open configuration, we use negative sign. For cross configuration, we use positive sign, because we already identified that our 4-bar linkage is open configuration. So the theta 4 angle would be 124.87 degrees. And if we just look at this diagram, which indicate or verify our calculated angle. In step 4, we need to find theta 3 using this equation, and for open configuration we use this equation directly to get the angles, and the angle we get for theta 3 is 85.67, which if we just look at this diagram, which also verifies that our calculated angle is close enough. Once again, step 3 and step 4, all the equations will be given to you, so you don't need to remember any equations. Once we find, so when we get theta 3 and theta 4, then we can find omega 3 and omega 4, which is angular acceleration of coupler and angular acceleration output link, using these two equations. Because we are given all the dimensions that we needed and we calculated theta 3 and theta 4, we have all values to calculate omega 3 and omega 4, and I found these two values. Feel free to pause this video and calculate yourself and match with this number. So this is our first part of our answer, where you're asked to find angular velocities of coupler and input link. Regarding of calculating angular acceleration, once again you will given these two equations. Now from this equation you can see you need to find A, B, C, D, E, F, these values, and these parameters are also given by these equations. So we have these using this table, and we have these equations. We can easily find the values of A, B, C, D, E, F. Once we find these values, we put these values into the equations for alpha 3 and alpha 4, and that would be our second part for second part of A, which are where you asked to find angular acceleration of coupler and output link. So up to this, all the equations will be given to you. You need to just identify correct link length, and you need to identify which configuration you are given. Once you identify these two important factors, then it's really simple, just using this equation, and you can find whatever you are asked for. In part 2, you're asked to find linear velocity of pin joint A and B. So for linear velocities and linear accelerations, the equations will be not given to you, so you need to derive the equations and then you need to find respective linear velocities. Alright, so let's start with this one, where we draw let's consider that OA is a vector whose length is r, and it makes angle theta with positive x-axis counterclockwise. If that is so, we can represent position vector as r equal small r e j theta in a polar form. Now, by definition, if we differentiate this position vector with respect to time, then we'll get velocity. So the differentiation is of r j e j theta e theta d theta by dt. Now by definition we know that angular velocity equals to angular position with respect to time, so we can write this bit as omega. So ultimately the linear velocity equation becomes r j omega e j theta, which is in polar form. Now we want this expression into Cartesian form by introducing Euler identity. So the form becomes cos theta plus j sin theta. Once we multiply this j with this parenthesis, our equations become r omega minus sin theta plus j cos theta, because we know that j square equal -1. Alright, so this is our generalized equation for any point, linear velocity equations for any point or any pin joint. Now in our problem, the second task is to find linear velocity for pin joint A and pin joint B. That means you are asked to find VA and VB. Now if we just look at our forward linkage, we need to identify what is that velocity is related to. So for pin joint A, it's the connection between link 2 and link 3. So when it say VA, it means VA2, which is a pin joint, and this is our pin joint O2. That means you're asked to find linear velocities of pin joint A, which is relevant to link 2. So the equations for VA will be the length of this link, which is A, the angular acceleration of that link, which is omega 2, and then negative sine theta 2 is the angle that relevant to the link 2, so sine theta 2 plus j cos theta 2. And for VB, it would be related to link 4. So all the dimensions and will be relevant to output link. So the length of the link is C, the angular acceleration of that link is omega 4 minus sine theta 4 plus j cos theta 4. So at this stage we know all these values. So once we put all these values, we should able to get VA and VV in terms of complex number. So when I put all the relevant value of link 2, I got the expression as negative 11.314 plus j 11.314, which is a complex number. So we need to find the magnitude of this linear velocity, and which we can do by just square root of these two terms. So 11.14 squared plus 11.314 squared, and the magnitude we get as 16 millimeter per second. Alright, so that is our magnitude. Now we need to find angle. So let's consider this is a phi, and we need to calculate as tan inverse y component or imaginary part divided by x component or real part. So it's 11.314 divided by negative 11.314. So ultimately the phi we get as negative 45 degrees. So let's draw a tiny diagram where x-axis represents real number, y-axis represents imaginary number. So if we just look at here, so our real part is negative, so it should be somewhere here, and our complex part is positive, so it should be somewhere here. So when we calculated this 45 degree angles, it's actually these angles, and this is our vector VA. So according to definition of vector, we need to measure angle at root of the vector, which is here, with positive x-axis counterclockwise. That means we need to get these angles, and to get these angles, our angle for VA would be 180 minus phi, which is as a result is 135 degrees. So and that would be our answer for part B, where you are asked to find VA. So we found linear velocity of pin joint A in terms of magnitude and angle. Exactly same way we can find VB as magnitude, and first of all let's write down VB as a complex number, where we found 13.53 plus J 9.43. so that is our complex number, and then we get magnitude of VB as 16.49 millimeter per second, and in terms of angle we get tan inverse imaginary part divided by real part, and the angle, calculated angle, is 34.88 degrees or 35 degrees. Now let's again draw the diagram, tiny diagrams, where x-axis represents real number, y-axis represents imaginary number. Now when we look at our complex number for VB, we found that both imaginary and real part are positive, so it should be somewhere here and here. So the angle we calculated here is this angle, and this is the vector VB. Because it's in first quadrant and it's with the positive x-axis counterclockwise, so we don't need to change anything. So our answer for VB would be VB angle as 35 degrees, and that is our another answer for part B, VB. So just a few minutes ago we found this expression for linear velocity in polar form. So once again, if we differentiate this linear velocity with respect to time, we'll get acceleration, linear acceleration, and when we differentiate this part, we'll get dt in parentheses r omega j e j theta. Now in these parentheses you can see that r and j are constant with respect to time. However, omega and theta are variable, two variable which varies with time. So we need to differentiate using UV terms, where we used u, then differentiate v, and then we sum it with the second term where we give v as it is and we differentiate u. So in this way we can get rj. So we can write rj in parentheses ej theta. In this time this is u, and So our U would be EJ theta and V is omega. So first time we differentiate V or omega with respect to time, second time we differentiate EJ theta or U with respect to time, and each time we keep this as a constant. So after the equation becomes this. Then if we want to simplify it, multiplying this Rj with this both term, we get R alpha J EJ theta negative R omega square EJ theta. Now just two important note. One is J square equals to -1. The other is, by definition, alpha equals to d omega by dt, and that's why when we differentiate d omega by dt here, we find alpha. Alright, so when we simplify this polar form, then we are ready to convert this into a Cartesian form, and after converting the Cartesian form, the equations become this. Once again, simplifying this, we get R alpha negative my apologies, it should be cos theta plus j sine theta. So ultimately our equation would be negative sine theta plus j cos theta negative R omega square cos theta plus j sine theta. And once again, this is our generalized equation for linear accelerations. So once we derive these equations, then we need to identify which link we need to consider to find the relevant pin joint. So for A, which is a pin joint A, and this is relevant to link 2. So in these equations, the length will be linked to, angular acceleration will be linked to, angles would be relevant to link 2, angular velocity will be linked to. So we know all these values. Once we put these values into these equations, we should get a complex number. So when we replace all values of relevant to link 2, we found AA, which is a linear acceleration of pin joint A, as a complex number like this. So the magnitude of this pin joint acceleration would be 128 millimeter per second square. Once again, we need to calculate the angles, which is negative 90.51 divided by negative 90.51, and the calculated angle is 45 degrees. And once again, we need to draw this diagram where x-axis represents real number, y-axis represents imaginary number. Now this time our real part is negative as well as imaginary part is negative. So the angle we calculated is this angle, and this is our linear acceleration AA. So once again, we want the angle with positive x-axis counterclockwise, so the angle should be with this one. So our pin joint A acceleration angle would be 180 degree plus phi, so ultimately the angle would be 225 degrees, and that is your answer for task 3, which is linear acceleration of pin joint A. In exact same way as we derive the equations for linear acceleration, we can find AB as a complex number, which becomes negative 285 minus J 254, 0.51, and the magnitude we get as 382 millimeter per second square. Phi, we get phi as 41.68 degrees. And if we just once again draw this tiny diagram and try to represent the vector, then we find that this is our vector. However, we want to make it with positive x-axis, so our angle would be 180 degree plus 41.68, so the ultimate angle would be 22 degrees, and that is your answer for part C of pin joint B. Now, what happens when there is a point on a coupler? Let's say this is P, this is pin joint A, this is pin joint B. So what happens if we have a point on a coupler AB? How can we find the equations for point P? Let's consider linear velocity of point P. So as a VP, the expression would be linear velocity of A with this one plus linear velocities of AP, this vector. So now this vector makes theta 2 angle, and this vector, this is positive x-axis, this is theta 3. Let's say this pin joint makes angle with AB or coupler as delta 3. So the expression for linear velocity, we know that the length of this respective vector and then length of this respective vector, angular acceleration of respective vector, then angles of respective vector. Okay, so exactly same way for AP vector. So AP vector, the length is given to you. You should know this length. Let's say in this case we know as R, so it should be R. Now because the P is on the coupler which is link 3, so the angular velocity would be relevant to link 3, so we wrote omega 3. And when it comes to angles, we need to consider once again, according to definition of vector, we need to measure angle at root of the vector with positive x-axis counterclockwise. In that case the angles is this much, which is delta 3 plus theta 3. So negative sign delta 3 plus theta 3 plus J cos delta 3 plus theta 3. Alright, so let's consider that now N is a point on an input link and Q is a point on output link. So O2N and O4Q is two vectors. To get their linear velocity of these points, what we can write down as the respective link length. Let's say this is length N, and let's say this is length Q. So for Vn, the linear velocities of this point N, we can write N, the length of the link, and angular velocity of that respective link, which is length 2 in this case. And for angle, we need to write down as theta 2 plus delta 2. Now delta 2 makes and delta 2 is an angle between O2N vector and O2A vector. So the total angle that we are looking for is this angle, which is delta 2 plus O2 theta 2. For O4Q vector, the angle would be this one. Now because we don't know this angle, so we can write down as theta 4 minus delta 4. So the angle for this vector O2n vector is sine O2 plus delta 2 plus cos theta 2 plus delta 2. For Q point, we can write the linear velocity of point Q as the length of this vector, which is Q, relevant angular velocity of this link, which is link 4, omega 4, and the angle should be theta 4 minus delta 4 plus j cos theta 4 minus delta 4. So once again, these values should be given to you, especially the length of the vector and the angle that makes with the relevant angle. These two information should be given to you, and then definitely you can find the values. Alright, so that is the end of today's tutorial, where you find how to get angular velocities and angular accelerations for a given four-bar linkage, where you will given all the equations for linear velocities and acceleration of any pin joint or any points on the links. You need to derive the equations, and then you need to find the magnitude and angles of that respective linear velocity and accelerations. Hope that will help you. I'll see you next week. Thanks.